Welcome back. Let us start lecture 10. So, we were discussing symmetry point groups, and in that discussion, we have already covered single axis rotation point groups and no rotation point groups, right? So, now let us look at next in the category is dihedral point groups. So, what are dihedral point groups? So basically, dihedral point groups are carrying more than one axis of rotations. So carrying more than one axis of rotation. So you can immediately think of many examples that we have already discussed. So let us look at it one by one. So the first category is within dihedral point groups. The first category is DN. So typical elements will be E, CN, NC2, which are perpendicular to CN. Okay, so let me use the other bracket. Yeah. Okay, so ECN, where CN is the principal axis, and NC2s, which are perpendicular to the principal axis. So the example is, let me show you. So this is cobalt atoms, which is the central atom here, and then we have triethylene diamine, which are arranged something like this. So let me see, NH2, NH2. So it is clear that three NH2s are coming out of the plane of the board and three of them are going back to the plane, right? Where cobalt is sitting in the plane of the board, and then these are connected with diethylene group. Okay, so you have this and you have this. So you can easily see that the central cobalt atom actually has the octahedral geometry, but because of this diethylene group, this actually does not belong to octahedral point group, but DN point group, right? So you can see that where is your C3 axis? There is a C3 axis which is going like this, so which is going through the plane of the board, perpendicular to the plane of the board, and which will be rotating these NH2 groups 1 2 3 and then 4 5 6, and then there will be three C2s which are perpendicular to this C3. So that means there will be a, so can anyone tell? So you can think of, maybe, so you will have one C2 which will be, so this is now in the plane of the board. So if I do this rotation, this NH2 will come to this place and this NH2 will go to this place, right? So similarly, you have another C2 like this, and third C2 will be like this, right? Right. So that's one example. Then we have another example which is called as ferrocene. So ferrocene is a molecule with two 5-member rings with an aromatic character and then a central metal which is iron. And now the second ring is not exactly eclipsed or staggered with this one, but there is a slight angle to it. I'll just draw it like this, and then there is coordinate bonds like this. So I understand that it is not clear, so because it's a 2D plane, so I request you to go to chemtube3d.com and under symmetry tab, find this molecule under DN point group or D5 point group. So maybe other way of drawing this molecule will be, let me show you. So is something like this. And then let me draw the other ring as in color red. So there is a slight angle to it. I hope you can all see that now. And then so red is behind the plane of the board and blue is in front of the plane of the board, and in the center iron is sitting, which is in the plane of the board. Okay, so this is your iron. So now if you see that there is where is your axis? So C5 axis is passing right through, perpendicular to the plane of the board. So you can draw it like this, and then you have 5 C2s which are perpendicular to this. So 5 C2s will be bisecting through this. Okay, one. Similarly, you will have another C2 bisecting through this. So you can see that the one carbon atom is slightly to the right, the one which is behind, and the one which is in front is slightly to the left. Similarly here, so you have one carbon atom slightly to the left, another to the right, and C2 is passing right through between. And similarly here, so you have 5 vertices, so 5 such C2s. So basically it has C5, 5 C2s which are perpendicular, and E, right? So this example, it can be very well understood now. And if you cannot visualize it in 3D here, so I request you to go to chemtube3d.com and try to visualize the molecule there. Both the molecules are listed in that website, and it will be easier for you to understand if you log in. So this is one of the dihedral point groups. Now let's look at the second dihedral point group, which is DNH. So as the name suggests, so it will have E, Cn, again 5 C2s which are perpendicular to Cn, and in addition to that there will be a sigma H, right? So in the previous case there was no H, so H is denoted as DNH here. Now we have already seen this example. One of the example is BF3. So we know that there is E. We should be able to locate C3, so I will not spend time on that. And then we have 3 C2s and we have sigma H, right? So that is very, very clear. Sigma H is the molecular plane in the plane of the board. C3 is the perpendicular to the plane of the board, and then C2s will be passing through 3 BF bonds. So that should be very, very easy. Then we also have seen, or we have not seen, but let's see, eclipsed ethane. We have seen the case of staggered ethane when we were discussing S6 axis, right? So in this case, let me draw the one with a slight angle, but there is actually no angle to it. It's right behind. It's unlike twisted ferrocene. Twisted ferrocene had a small angle, but this one is, the dotted line is right behind the solid line. Okay, so you have H. You know how eclipsed ethane would look like, right? Okay, so now here, so this thing would also have E, C3, 3 C2s, and sigma H. Now here the C3 would be passing through CC bond, right? This one will be your C3. Then 3 C2s will be bisecting the CC bond and will lie somewhere in between the two hydrogens. So it's like it is not passing through CH bond, it's actually bisecting the CC bond. Okay, so it's in the plane of the board while 3 hydrogens and this carbon is actually in front of the plane of the board, and the other methyl group is in the back of the plane of the board, right? While the three C2s will be in the plane of the board. And sigma H is also in the plane of the board, which is bisecting the CC bond, right? Okay. And then in addition, it will have some other planes. So, but these are the minimum criteria for having DNH, right? So, for example, this one also has sigma V's or sigma D's. So this one will also have sigma V or sigma D, but let's not worry about that. This is the necessary and sufficient condition for it to fall under DNH category. So now let us see the next category in dihedral planes, which is DND. So DND has E, Cn, NC2s perpendicular to Cn, and N sigma D, and in addition it also has S2N. Okay, so sigma D contains Cn and bisects 2C2 axis, right? That is as per the definition of sigma D. Now an example, we have already seen this example. We know staggered ethane, right? So I'll just quickly draw it. So we have already discussed this example, so we will not cover this in detail. So it has E, C3, we know it has C3, it has 3 C2s, it has 3 sigma Ds, and a S6, right? We have seen how there is a S6 in this one that we have already seen. Okay, so let's move ahead, and in the next in the category is D infinity H. Okay, so the elements and the corresponding operations will be C infinity. This is actually very easy to identify. Infinity C2s which are perpendicular to C infinity, and then we have sigma H, there is S infinity, and there is I. And the typical characteristic of this molecule is that they are centrosymmetric linear molecules. So linear molecules can either be non-centrosymmetric or centrosymmetric. There are only two options. We have already seen C infinity V, which is non-centrosymmetric linear molecule. So this one is centrosymmetric linear molecule, and a typical example is C double bond CO2. Okay, so the center of symmetry lies at the carbon, and then you have two oxygens at the end. So you can easily see where is your C infinity axis. C infinity axis is passing right through the OCO bond. Then you have infinities C2s perpendicular to this. So axis perpendicular to this. So you'll have one axis, another axis, another axis, right? So there'll be infinity such axis passing through perpendicular to OCO bond and so on. Each of this will be a C2 axis. And sigma H, there is one sigma H which is perpendicular to the plane of the board and cutting right like this. Then you have S infinity and I, which is also very easy to see. S infinity will be this axis, collinear with C infinity, S infinity, I will be at the center. So the molecule is very easy. So centrosymmetric linear molecules will always be of D infinity H point group. Okay, so that finishes dihedral point group. Let us now look at next category. Next category is very simple, but The examples are difficult to find in this group, S2N group. Okay, so within S2N, let's or it's actually called as not S2N, it's called as SN point group. SN. Okay, so within SN, let us see an example of S2N. There is only one category, S2N, for E1N basically. This will have E, Cn, and S2N symmetry element. There are no other symmetry elements present, no sigmas. So, a typical example, it's actually a little tedious to draw. Let me see if I can draw it correctly. Now, this particular bond is coming out of the plane of the board, and so is this one. Every alternate bond is. So it's something like a chair form of cyclohexane, but this is cyclooctane. And then you have four fluorine atoms attached to it, which gives it asymmetry. You can have any atom basically here. So you can see now there is no sigma present to this, because even if you try to draw a sigma cutting, let's say this one, you'll not be able to reflect the opposite atoms here, right? Okay, so there is no sigma, very clear. There is E, there is Cn. So in this case, what will be your Cn? Try to find out. And then you will have a S2N. So try to locate Cn, try to find out the order of Cn and S2N in this case. Let us take it as home assignment. And if you have any difficulty, come back to me. So find out order of Cn and S2N axis in this molecule. Okay. I have one more example for SN point group, which is also a little difficult to draw. Let me see if I can draw it correctly. So now the phenyl ring, there are 4 phenyl rings connected to it, but these are not in plane exactly. This one is something like half of the ring is coming out of the plane of the board and half of the ring is going back. So something like a propeller. Similarly, this one also. So here, in this case, I'll tell you what the order is: E, C2, S4. It is easy to identify. So this one is also S2N point group or S4 point group basically. Okay. So this should be very, very clear. So we have covered single axis, non-rotational, dihedral S2N, and last in the category of point groups is called as cubic point groups. So these point groups, these are little special in the sense that they are formed by something called as regular polyhedra. The shape of these molecules is can be represented by regular polyhedra. So let us first try to understand what is a regular polyhedra or polyhedron. So what is a regular polyhedron? So regular polyhedron has, let me open up my figures. Yes. So the faces are face. So regular polyhedron is a closed figure, the face of each polyhedron, or all the faces, are equivalent. Vertices are equivalent. When I say equivalent, I mean that they are equivalent when you operate them by symmetry operations. So all the faces are equivalent, all the vertices are equivalent, and all the edges are equivalent. So that means you can replace any edge by another edge by doing any kind of symmetry operation, and they should be equivalent. Okay, so how do you form regular polyhedrons? Let us see that. So what it takes to form regular polyhedron. So for a polyhedron to form, you need to start with a equilateral triangle. Okay, so let's say if we start with equilateral triangle, how many equilateral triangles do we join together at a given vertex so that it can form a non-planar geometry? So let's say if we join two of them, then it will form only a planar geometry. So it has to be more than two, right? So more than two meaning, so this will not form a regular polyhedron. However, if we have three equilateral triangles connected, so two are depicted on one on this side, another on this. Let me draw it a little bigger so that you can visualize it clearly. So this is one, this is second, and the third one is at the back. Okay. So this is your this is my one triangle, one equilateral triangle. Then I have second equilateral triangle, and third one is at the back, right? These are the three which are meeting at this particular vertex, right? And then the fourth one automatically goes at the bottom of this, which will seal it and make it as a closed figure. So what is the geometry of this? This is basically a tetrahedral geometry, or you can call it as tetrahedron, right? Now so we combined two equilateral triangle along the edge. You cannot do it, or at the vertex, so you cannot make a closed figure. If we combine three, you can make a closed figure, and this is a regular polyhedron. Now if you see all four faces, it has four faces which are all equal. How many edges are there? 1 2 3 4 5 6 edges. All six edges are equal, all four vertices are equivalent, right? So that forms a regular polyhedron. Now let's say if we have if we combine these equilateral triangle, if we combine four equilateral triangles at a vertex, so that will give rise to a, how do I draw it? Let's see. Now it will be easier to draw if I first draw a, so you can see that now there are four faces on the top, four equilateral triangles on the top, and four equilateral triangles at the bottom. So this forms a octahedron. This also is a closed figure, right? So it has 8 faces. Now similarly, if we draw 5, so here at a given vertex, four equilateral triangles are meeting. So one is at the back, one is at the front, and then you have one at the side and one at this side, right? So you have 4, and similarly 4 at the bottom. So at a given vertex, at any given vertex, there are 4 equilateral triangles which are meeting. So now let's see if we can go to 5 equilateral triangles and we can make a closed figure. So let's try to draw it. So far we are playing only with triangle. Then we'll have to go to the higher polyhedra to see if we are drawing it correctly. Yes, anything which is at the back, I'll draw it with a dotted line so that it is not confusing. So if you notice, at any given vertex there are 5 faces which are meeting. One, two, three, and then you have 4 more. And this one will be meeting. Let's draw this a little bigger. So imagination is the key here. Okay, so now if you see, at each of this vertex there are 5 equilateral triangles which are meeting. So let's try to count. So let's say if we are looking at this vertex, so you have 1, 2 and 3 sides, and then 4 and 5, right? So pick up any vertex. So here also it is easy to see at this one. We have 1, 2, 3, 4, 5, right? Similarly here you have 1, 2, 3, 4, 5, right? Here 1, 2, 3, 4, 5. Okay, so this particular figure is called as icosahedron. So here you have 20 equilateral triangles or 20 faces forming, and this one is also a regular polyhedra, so it falls into the definition of regular polyhedra. So now let's also see, so if we try to combine more than 5 equilateral triangles at a given vertex, you cannot form a regular polyhedra. It will not fit into a regular geometry. So these are the only possibilities which can be formed by a triangle or equilateral triangle. Let's also look at what can we do with a square. So if we have a square, so if we combine 2 squares, you cannot do it, right? If you combine 3 squares, you still cannot do it. So you have to, no, you can do it actually. With 3 squares you can do it, but how do you do it? So how do you do it with the 3 squares? You actually form a cube. So here if you see, at each vertex there are 3 faces which are connecting. At each given vertex there are 3 faces which are connecting. So this also forms a regular polyhedra, and this one is easy, so you know that this is a cube. And if you try to combine 4 these things at a vertex, then it will form a planar structure again, right? It will no longer form. So this is also not a possibility. So with square, the only possibility is a cube. With triangle, there are 3 possibilities. Now let's go to a higher polyhedra, even higher polyhedra. So let's go to 5 sides, a regular pentagon. So now if you try to do it with a regular pentagon, you end up forming a something called as dodecahedron. How do you draw it? So it's actually easy. If you see that if you slice the vertices here, I'll just try to do it for you. If you slice the vertices here, you will end up in a pentagon. So all these vertices, if you slice at equal lengths, you will end up pentagons joining each other. Let's try to draw it so that it is clear. Now try to draw 5, all of them connected with each other. We have 1, 2, 3, 4. So this one is 5th. So drawing a 3D figure on a 2D is sometimes a problem. So let's see. And then you have at the back each of this is connected. So now you see that at each vertex, at a given vertex, there are 3 faces, 1 face, 2 face, and 3rd face. At each given vertex, that there are 3 faces. So similarly here, if you see that 1, 2, 3, you see it here, there are 1, 2, 3. So there is an interesting relation actually. If you slice this one along the vertex, you'll end up in icosahedron, right? So this thing is related to this thing with the slice operation. It is not a symmetry operation. This is just for understanding. So this is related with the slice operation. Similarly, if you cut cube along the vertices, you'll end up in octahedron. So this one is also connected with a slice operation. So that means these two will have same point group, because you can fit octahedron inside a cube, or you can fit cube inside a octahedron without actually worrying about the symmetry. Similarly, icosahedron can be fit into dodecahedron, and dodecahedron can be fit into icosahedron, right? So I'll try to draw it little quickly and then we can stop for today. So let's see, if you have a cube, you can see that how the 6 points at center of the 6 edges will actually form a octahedral geometry, right? So it is very easy to see. Similarly, within octahedral, you can fit a cube. So this leads to a set of point groups called as cubic point group. The name is cubic, but it has non-cubic entities also. So the point groups are, we will see in more details later on in next class, but I'll just list down: tetrahedral, octahedral, icosahedron, and so on. So we'll see little more details of it, but I hope it is clear that how these regular polyhedrons are formed. So any molecular shape which is related to these shapes can be categorized into these point groups. So why understanding these shapes are important? Because these are very highly symmetric point groups, and the number of operations are huge, and it is difficult to list down all the operations at times. But if you know that the molecular shape is closer to any of these shapes, so you can immediately identify, and then you can try to locate all the point groups, right? Okay, so that's all for today. So let's continue in the next class with more details of what are the symmetry elements and operations for these point groups, and what are the other categories within cubic point groups. Okay, thank you very much.